Okay, so let's continue to the next topic. We kind of ended up of talking about the coordinate reference systems in our previous tutorial, but let's now dive a bit further into the topic here. I guess these projections, are you all familiar with them? Yeah, hope so. I guess, how often have you kind of needed to really do some stuff with projections? ArcGIS does quite a lot of stuff automatically, so you don't actually need to do anything. But have you had any kind of issues that has been because of projections? Yeah, because sometimes, you are kind of, you have a situation when you are doing something and then you're like, why is this not working? And in some cases it might be that the projections are behind the problems that you have, so they might be in a different projection, and then you try to do some analysis between them, and then basically the coordinates doesn't align, and that causes some troubles. But as I said, ArcGIS does quite a lot of this automatically, so it's kind of in the background, it on the fly reprojects stuff and make sure that the data sets that you have, they need to be on the same projection, so when you are doing different tasks. But in Python, as we are doing it in a programming way, you need to take care of yourself these things, that the data sets and the geodata frames are on the same coordinate system. There will be warnings, so that okay, these two geodata frames seems to be in different coordinate reference system, so it warns you, but it doesn't actually do anything, so you need to do it yourself. So it's kind of important to be aware of the projections. Luckily, as you saw earlier, so defining a projection in geopandas is fairly easy. The tricky things comes when you have some really, well, it's not tricky, but you might need to kind of use a bit different approaches when you have some specific projections, such as, well, this kind of Lambert azimuthal equal area projection, which is the kind of European Commission standard for presenting EU level data. So in those cases, you might need to kind of use some different tricks to actually do the projection, and especially when saving the data. So let's see how we can do. There is a note like, what is a good projection? That is a whole question of its own. I put a couple of links in here that basically can give you a bit of more detailed explanation about, well, what kind of properties different map projections have and what are the strengths and weaknesses of different map projections. So when choosing a map projection, it depends on your, like, what you are trying to visualize. The really unfortunate thing, for example, is that if you go to Google Maps, at least it has been like that. So what they use as a projection is a web Mercator. And take a look at the shape, for example, of Finland and how big Greenland is compared to, for example, Africa. So this kind of distorts the real dimensions of the world in a quite awful way, and it's really unfortunate that they use this as a map projection. So use something else than web Mercator when doing things. That's my advice and hope and wish. But yeah, so basically it depends quite a lot, like of your question, what you want to actually show. So Web Mercator kind of shows the directionality correctly, but quite often if you're doing some global maps, you might want to actually try to show different countries so that their area is more or less correct. Or then you might have this equidistant map that tries to have that kind of projection where the distances between places are more or less accurate. We will actually, during this tutorial, we will see how we can do this. We will measure some distances between Helsinki and some other places in Europe, and we will use that kind of projection for that. But yeah, so there are different properties of projections that you might take into account when choosing the thing. But of course, as I said, so it depends on what you want to show on a map, and then it also depends on the spatial scale. If you are doing global map showing some stuff, it's kind of more critical when compared to if you show something, for example, inside Helsinki region, for example. If you are using Web Mercator, it's not good, but like more these kind of metric systems targeted to this area, it really doesn't make that big of a difference when which one to choose from. But yeah, so there is a link of that, and then there is also a nice link, another one kind of discussing about what's the best map projection. And this guy or these guys, well, they chose one, but they have quite nice these kind of visualizations that shows like how distorted different projections are, and so on. So if you're interested, and I hope you are, at least geographers usually are, so take a look of those two web pages to read more about the projections in general. But for this part of the lesson, we will work with Europe, the borders of Europe. So we have the European countries, and we will do something with those. And in a similar manner, let's download the data, and then we also extract the data. So again, with 7-chip, extract to folder Europe borders. It should work. Yep. And here we have again a shape file with all the necessary files, and we can start by reading the data in and seeing what we have. So read the data. First we need to specify what is the file path. So I just copy and paste again this folder name, and then, as I mentioned earlier, the file name that ends with .shp is the one that you want to put here when reading the data in. And then we can read the data with the GPD, so geopandas read file function, and in this way we should have our data that looks like this. So what we will have here, we only have two columns. We have the time zone ID, so it seems to be presenting time zones, these different for different countries and areas. And then we have the geometry, so fairly simple data frame. We can also take a look how does it look like. Hopefully this will not take too long now. I will plot it. I will say that face color equals to white. So in this case I will just say to the spider or the geopandas that use one color for each polygon that we have, and it should be white, and then the edge colors should be black, and they are by default like that. So hopefully it goes a bit faster now than before. But we can take a look at this. So yeah, now it comes. Didn't take too long. Yeah, so what we have here is that we have this map of European countries. So we have Finland here, UK, Spain, and so on. So this kind of area, and what we can see from the X and Y axis is that the coordinates indeed seems to be in latitude and longitude. So we are somewhere here with northern than 60 degrees and somewhere around 20. So that is what we have here, and of course we can check the CRS, so the coordinate reference system, again by calling that, and we can indeed see that okay, it is the EPSG 4326. So I don't fancy this kind of map because it distorts countries. So what I would like to do is to indeed use the map projection that European Commission kind of recommends, which is this Lambert azimuthal equal area projection. So how can we do that? There are few links in here. So we can basically specify and transform and reproject our data frame into a different one quite easily. And the easiest way of choosing the kind of target projection for your data is indeed to use these EPSG codes, as I mentioned before. There are few pages that are really useful for exploring these. One of them is the spatialreference.org, that basically is this kind of page that has lists all the EPSG codes and information about them. So what we could do, for example, is now to find out the EPSG code for this Lambert azimuthal equal area. So what we can do is to find it from here. Let's see what we have. Then it lists quite a lot of different ones that are close to it, it seems. What we are looking for here is actually this ETRS LAEA. It stands for Lambert azimuthal equal area. So this is the one that we are interested in. So the EPSG code seems to be 3035. And from this page you will find a lot of information about the projection itself, the VGS84 bounds and so on. And also information about the actual PROI4 text and so on. So we will actually see these and go through these, but these are these kind of definitions of projection that we need to add and say to GeoPandas what to include. It doesn't need to be this complicated, but sometimes it is when we want to specify some more not so common projection for the file. There are also some other tools that might do things more easier, but I decided to show you this as this might be useful in some cases. So let's continue. So now we know that the EPSG code for the projection that we want to use is 3035. So let's see how we can make a projection with our data. First of all, let's create a copy of our geodata frame, and I will call it data Troy, which is like projected. And how you can create a copy, like a full copy of your geodata frame or data frame, is to use this data.copy command. And what this does is it basically creates a similar, so it creates identical copy of your data frame that you used in here. And with this one, I basically asked from geopandas that are the values equal in different indices, and it seems to be that they all are. So let's do so that we project our data into this EPSG 3035 projection. And how we can do that is to use a function called toCRS. So again, really simple stuff to do, but quite useful and powerful. So toCRS, this is a function that you can use to define different projections, and as a parameter this function takes the EPSG code as such, as like this. And basically what this will now do is that it transforms the geometries into that new projection. So this is the original one. We can see that there are the latitude and longitude coordinates, and when we compare that to the new projections, we can see that what it did was that it transformed these values into that new one. And let's take a look of how our data looks like now. So again, I will do a plot. Face color, let's say that the color wants to be blue, and it takes some time again, but we can. So this was the how it looked like originally. We can, so we had that kind of map, and let's wait a bit and see how it looks when we reprojected the data. Usually this is not this slow, but it seems to be today for some reason. But yeah, now we can see that we got this kind of map, which is, well, the shapes of the countries are, at least for my eye, quite much better. We can take this as a reference here. So we can see that we indeed transformed the geometries into this kind of metric system that looks quite a lot better than this one. So Finland, the shape of Finland, for example, is more or less that kind of that I have used to see Finland as, and other countries as well. So doing a projection, reprojecting data in geopandas, it's as simple as this. So using the toCRS and defining the EPSG 3035 code inside there, and you can basically do projection from different one to another quite easily. Yeah, what is then? One thing that is quite useful in some cases is that as I showed you in here, there are these kind of, this is just a piece of text, and this is basically kind of represents the projection of the format that we had there. So what you can do is that you can actually copy and paste this information from here and put it inside a string here. So let's say proj for txt. So this is just a kind of a standard way how these projections are actually presented in the data. For example, when we take a look at this .brj file, is that you have something like this inside, and this is basically the information that the for example ArcGIS and the different GIS softwares uses to basically say that this is now in VGS 84. So you have information about the datum, what is the unit, so this is the degree, decimal degrees here, and so on. And there are different ways of presenting that same information. So that is what comes with shapefile typically. There is this proj4 kind of way of saying that. It looks a bit different, but it is exactly the same information. Then there is this kind of well-known text and so on. So they are basically showing the same stuff, but with a bit different format. So just that you know that these are available. So what we can indeed do is that we can actually do the same projection using this proj for txt. And actually I could show you the proj4.org. So this is basically a standard in all GIS that is basically behind and showing the projections for different software. So this is the kind of package that keeps the projections for different projections, so the kind of information about them. And you can basically, there is a list of all different projections inside, and there are actually quite nice visualizations showing that this Eckert 5 seems to give this kind of map. And let's take a look at the one that we use, Lambert azimuthal equal area. So it seems to be something like this, and we focus on Europe in here. We will shortly see why this might be useful, but let's first check that do we get the same kind of projection if we use this data to this text in here. So we can say that again, use the data and to CRS. So what I will do now is that I will again project the data into the same projection, but instead of using the EPSG code, now I use the actual the raw data or the raw text in here. So I will say that proj4 underscore txt, and yeah, I need to define it first. And then what it does is that it should do the exactly same projection, but now using that text. Let's say keep the head of 2, and let's take the original one. So these numbers should be same, and indeed they seem to be. So 341, yeah. So these are kind of different ways how you can pass information inside there. There are also other ways, but these are maybe the useful ones. And now, why this becomes handy is that I want to just give you a kind of practical example. So the idea here indeed is to calculate distances between Helsinki and the centroids of different countries in Europe, and centroids basically of these polygons in here. So what we want to do here is that we want to use a specific projection called world equidistant cylindrical projection, and it is this kind of, so again using the spatial reference, so you can basically Google and you will find these pages, so that's maybe the easiest way of finding the projection files. But basically this is the projection that we want to use. So this basically gives the distances correctly between Helsinki, which will be set as the center point, and from that everything is projected in a way that the distances are correct. But as you can see here, this is not actually available on this standard EBSG code. This is some specific ESRI format, and it might be, yeah, so it's a bit, so we cannot use the, for example, this from Fiona.crs from EBSG. So we cannot use this function, which was really easy to do the definitions here. But what we can do, because this is the ESRI kind of specific format for having the information, but what we can use is exactly the one that I showed you. So we can use this PROI4 information as a text, and we can basically feed this into the into GeoPandas. And why we need to actually use this as another reason, let's just say PROI for TXT LAEA. So how this projection works is that if we take a look at this, so how this world azimuthal equidistant projection works is that you need to specify the location where you want to target your map, and that will be the center point, and you will use that as a kind of, that distances to this point will be correct, but if you use some other place it wouldn't be correct. So we want to specify the location of Helsinki as input. So this actually have these parameters, this false easting, false northing, central meridian, latitude of origin. So what we can do is that as we have this text in here, so this have some information, so this gives that projection is aerial equal whatever that was, azimuthal equidistant. And here we have these parameters, lat 0 equals to 0, lon 0 equals to 0, then we have x 0 and y 0. So these are, and here we have units that are meters. So as an output of this projection, you will end up having meters. All the measures will be meters when you do calculations. So what we want to do is that we want to actually specify kind of the center location to Helsinki. So we want to give a latitude value of Helsinki and longitude value of Helsinki inside here. So let's do that. So I don't remember by my memory what are the longitude and latitude, but I just copy and paste them from the website. So it seems that the latitude, well, coordinates of Helsinki. So the Helsinki longitude seems to be 24.9417 more or less, and the latitude is something like 61666. So what we want to do is that we want to insert these values inside this definition here, and what we can actually do is that I showed you how to use the format for doing string manipulation, so we can actually take use of that. So we can modify this text a little bit so that we specify these curly brackets and say that this is the first item in this format function, and the first item that we want to put here, well, it's the latitude, so we want to specify that HKA, so Helsinki latitude, should go there. So let's say HKI latitude, and then on the longitude I want to specify the Helsinki longitude, which is this 24 something. So HKI lon goes there, and when doing this, just say Helsinki. Yeah, first I need to put these into IPython, and then I should have, now I use the Proi, so that's the format version. And now what happened was that indeed we used the format to actually insert these numeric values inside here. And with this definition we can actually use the projection that we want to use, so this world equidistant cylindrical projection where the center point is Helsinki. So in a similar manner as I showed before, we can say that data world azimuth to equal distance. No, world equal distant cylindrical vec. So let's do so that we reproject our data again. So basically what you should use now as an input is that you should basically specify it as the VGS84 inside here. And the original Europe borders here is in VGS84, so that works just fine. So we can say that 2C RS, and then we specify this as a parameter inside here, and then we should have, when we execute, we should have those as pre-projected, and let's see what kind of values do we have. So yeah, now we have some minus blah 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 coordinates here. Well, they don't tell much, but if we again plot this thing, so we might maybe understand a bit better how this thing works. Takes a while, maybe I show you from here. What we will end up having is this kind of map. So when we plot the thing is that we indeed have the 0 and 0 kind of location. It is somewhere around Helsinki area here, and the distances are kind of from that point onwards, and these are meters, so from meters from that point east, west, south, north, and the distances should be quite accurate with this projection. So with this, now we got a map out of it. So indeed we got the same. And then what we can do is that we kind of calculate the distances. So what we want to do is that we want to calculate the centroids of each countries in here. So let's do that. So calculate the centroids of the countries in EU. Well, not in EU, but in Europe. And let's say that data VEC country centroid equals to data WEC dot centroid. Like this. So now what we have is that we have the original polygon in here, and then we have the centroid as a point, and the coordinates now are indeed those reprojected ones with the projection that we use, where the distances are correct. So okay, so now we have these centroids here, and now we would like to calculate the distance from these points to Helsinki. So what we need to do now is that we basically use the information from here and calculate the distance using Shapley distance function. So to be able to do that, we need to import from the Shapley geometry the point, so that what we want to do is that we indeed want to create this kind of Helsinki point from those point for Helsinki. So let's say Helsinki point equals to point, and the x and y, so HKI lon is the x-axis or the x value coordinate, and HKI lat is the y-axis. So this is, by the way, something that might be confusing every now and then, as the x and y, and usually when people speak about latitude and longitudes they say lat and lon, but actually they are like y and x. So just if your maps, when you are doing maps or presenting data and they look backwards, the most probable reason is that you have actually specified the x and y in wrong order into these objects. So now we have the Helsinki point, and it's just a point, and it should be Shapley point object, as we can see. So what I want to show you now is that how we can create a function where we actually calculate the distance between all of those points, and we take advantage of this pandas and geopandas function called apply. So I have written the function in here. I will just copy and paste it to my code, and I will explain it to you a bit better. Then I just run this. So what we have in here, there was a hint in exercise 6, I think, yeah, lesson 6, about this, using these kind of apply function and using your own functions within pandas. But let's go through that again, as we haven't actually done this before. So how you can use your own functions and do really efficient kind of run things efficiently is to use this kind of function called apply. So let's Google pandas apply. So there is this kind of function available that basically it applies a function along input axis of data frame. And this takes advantage of NumPy in the background, so it is really fast and efficient of doing iterations over rows or over columns in your data frame. So let's see how we can use that and basically use this function. That basically what this does is that it takes as an input one single row in our data frame. Then it takes as a second parameter the destination geometry. So what this does is that it calculates the distance between this destination geometry, which is a single point. So it is basically this Helsinki point that we have here. Then we have the source column, which is by default geometry. So the kind of in each row what column we should use for calculating the distance between this destination geometry. And then we have a third parameter, or fourth one, the target column. So to which column you should update the distance information to. So we can use this kind of approach to do the calculation. So first what we need to do is that as we have the Helsinki point, let's print it, Helsinki point. So we can see that these values are still latitude and longitude, but the our data frame, which was reprojected, so the information is in another projection. So what we need to do is that we really transform the Helsinki point, so these coordinates, into the same projection that where our data frame is at the moment. How we can do that is fairly simple. It is here. There are basically different ways of doing this, but how I will do that now is that I just create a geo-series. So I insert this point into geopandas geo-series, which is one column in a geodata frame basically. So create a geo-series of the Helsinki point. So how I can do this? Helsinki series equals to. So I can take advantage of this GPD geo series. And what we can use as an input, so we can actually put the values inside a list that we actually want to insert here. So what I want to insert is this Helsinki point, which is the shapely point object in here. And the second thing that we can actually specify when creating this geo-series is that we can specify the coordinate reference system at this point already. Before doing that, I will import the from fiona.crs import this from EBSG that we have seen a couple of times already. So let's just copy and paste it here. So we can directly say that this data that we put here is in latitude and longitude. The coordinates are in latitude and longitude. And now what we have when we execute this is that we have the same thing, but now instead of having the shapely object, we actually have geopandas geo-series kind of data type and object here. And why this is useful is that because now when we are saying that Helsinki series dot, now we have the two CRS function. So now we can actually reproject the point into different formats as well. So let's do so that we want to reproject that point into this same projection that we used for the other data frame. So Helsinki series, I just overwrite this and I say Helsinki series to CRS, and inside here I feed the projection proj4 txt information that has all the necessary details about our projection here, where Helsinki is the center point, and let's say now we should have it in the projection that we have defined for the other data frame, geodata frame. And indeed, earlier we had the coordinates as 24.94 and 60.1666. What you can see from here is that when we transformed it, now our coordinates are 0 and 0. And this is exactly what we want, as the Helsinki needs to be the center point and the distances should be away from that. So 0 and 0 is exactly the thing that we want. We could have made this also just by specifying and creating a geoseries or geometry with 0 and 0 coordinates, but I just wanted to show you this. And finally, one useful thing as well. So we have one item inside this series. So if we want to get the point object out of here, so get the shapely object from geoseries. So we can use this function called get, which basically gives you this Helsinki geo, or the point object from that as a value. So again, we are back in the same situation. We have point here, but now the coordinates are 0.0. And now what we want to do is to calculate the distance between this point and the all other points inside this data WEC. So all these country centroids that are on this one. And how we want to calculate them is to use this calculate distance function that we created here, that takes the destination geometry, which is basically the Helsinki point here, so point 0.0, and then we use the country centroid as the source column instead of geometry. If we would use the geometry, it would try to get the distance between the polygon and the Helsinki point, and I think that doesn't work. So they need to be. Actually, they might not. Let's test. But anyway, let's take the centroids and calculate the distances between those. And then the target column is distance. So let's do that. So apply the function to geodata frame. So we have the data WEC. So data underscore WEC equals to data WEC dot apply. So this is the function that you can use for running your own functions and applying those things to your geodata frame or data frame in Pandas. And how this function is used, so how you can basically run stuff from your own functions, is that you pass the name of the function that you have created and nothing else. So typically when you are using functions in Python, you say the function name, then you put the parentheses, and inside there you specify the different parameters. This pandas function, this apply, works a bit differently. So you just specify the calculate distance like this without any parentheses, and then you basically say that the destination geom, so this parameter, well, this equals to this Helsinki point that we have. So it is that shapely object from that attribute or variable. And then the source column, we want to specify that as well. So it is not the geometry, which is this polygon, but we want to use this country centroid in here. So the source column in our case will be country centroid. And the final thing is that where do we want to store this information? Well, we want to store it, by default it is stored in the column called distance. Let's say that the column name should be dist to Helsinki, so that it is intuitive right away. So in this way we can basically fill all these different parameters in this function. And what you might have noticed here is that we didn't specify anything for this row. So that is kind of left like that, so that you don't actually feed anything to that, because the rows of the data frame actually goes into that one. So that is something specific for this function apply. The last thing that we need to do is to specify that we want to iterate row by row the data frame, because you can also go like column by column with this function. So we specify that axis equals to 1. So this determines that we do the calculations and iterate over the lines row by row. So this is all we need to do, and let's hope for the best that things work. So let's try. So something happened and we didn't get any errors, at least. Let's see what we have here. Well, indeed we have this dist to Helsinki, and we have some numbers. Let's see what those numbers actually are. So what happens inside this function is that we actually calculate the distance between those geometries. Then we, because the result are meters, so we actually transform them into kilometers, and then we assign that result value into this target column that we specified to be this dist to Helsinki. So this is how you can use functions, your own functions in GeoPandas and Pandas using this apply function. And now it didn't actually, well, there is not big difference if you would iterate over using the iter rows function of Pandas compared to this, because we only had so few rows in our data frame. But when you start to have like hundreds of thousands of points or whatever, then it actually makes a big difference, because it's much faster to do it like this. Cool. So now we have some distance information. We can take a look a bit how far away from everywhere we are in Helsinki. So let's say, what is the mean distance to all other European countries that we have? Well, it seems that we are, on average, the distance to different countries are more than 1,100 kilometers, almost 1,200 kilometers. So we are fairly isolated and remote place in here in the north. But yeah, so these are some stuff that you can do, and basically that is the kind of content for this week. Then
I have a question.
Yeah.
For the place where you use the function, the source and the target, isn't it possible to like just do it directly and
like insert the number?
Yeah, enter the number.
Yeah, for sure.
New column, create a new column, and just calculate and just do that instead of using the function. So that's like the line.
So you mean, is it possible to, without using this function, to do that?
Just create a new column.
Yeah, it is actually possible to do stuff kind of row by row. Why I did this was in this way, because I wanted to demonstrate to you also this apply function that can be really useful in some other cases when you actually use kind of do more different kind of steps in between when you are doing things. But you can calculate, if we have the data, for example here, data frame. Here we have the polygons in here. So what you can do is that, let's say, took the data EC. So let's try, I actually want to try if the polygon distance works as well. So what we can do is that we can say data underscore WEC dot distance. So in a similar manner as you use buffer and other functions of the geodata frame, you can calculate the distance, and basically in here you can specify the Helsinki geo. And what you have here, let's see, I just pass this into yeah. So what you end up having indeed is that you have the same results in a similar kind of easier manner, but now the end result that you have is in meters. So what we did in this function is that we not only calculated the distance, but then we converted into a more easily readable format, so in kilometers the distance instead of meters. And the kind of good thing of this is, of course, easy way to do that, just to calculate the distance between these things. But the reason why using these functions at sometimes and quite often is that you can basically do more complicated stuff inside and do like multiple different things in one function instead of writing them in a separate commands in here. But the main idea was just to demonstrate how to use these functions. But as said, just using the data and dot distance and then the other geometry here, you will get also the distances between the other ones. And in some, maybe most cases, that is the easier way of doing things. So it was a good point. Cool. So yeah, maybe one notion still at the end. So basically, when calculating distances on Earth between places, so you could basically do this kind of approach of using this projection for each destination, but it is not actually so efficient way of doing things. So if you have a situation when you want to calculate distances between locations in different parts of the world, you want to use this Haversine formula. So this actually kind of calculates these great circle distances where the distances are more or less accurate, and there is actually a nice package in Python called Haversin that does that really easily, and you will get the result in kilometers or in miles or in different formats. So if this would be something that you want to do, so might maybe check this one. But we wanted to kind of see how you can do reprojection, so that is why we use that equidistant projection in here. So, but that's all for the lesson. So then we have the exercise 2, where you can actually start practicing these things. So what we have in exercise 2, we have again 3 problems. That should be, well, hopefully fairly straightforward. The first problem here is that we have this kind of starter script in here, and you should basically do some geometries and actually a polygon using these coordinates from these lists, and well, let's see what comes out of those.